Welcome back. In this lesson, we're going to be looking at how and why computers use binary to represent all forms of data. We're also going to be looking at the different types of number systems that are out there, denary, binary, and hexadecimal. And we'll be doing some maths to convert between positive denary and positive binary numbers. Finally, we'll look at how the use of registers, transistors, and logic gates allow us to represent data from the real world into binary data which the computer uses. Let's start with a did you know. Now, if you're interested in computing history, some of the names here, some of the ideas you might be familiar with. In that case, skip this part. But if not, we'll just go through how in the early days of computing, the only way to enter data into a computer was by flicking switches or by feeding in punched cards or punched paper tape. Computers weren't as user-friendly as they are right now. However, they still used to work with binary and data still needed to be represented as ones and zeros. So both switches and punched holes were easily able to reflect these two states. On represented 1 and off switch represented 0. A hole represented 1 and no hole represented a 0. Charles Babbage's analytical engine in the 1837 and the Colossus, which was used during the Second World War, were operated using punch cards and tapes. So you can see almost a century's worth of computing used to be done using punch cards, and these were very tedious to use. Imagine all of that program the lady is holding and you just accidentally knocked it over. It would take you a huge amount of time. And if you wanted to work out n factorial, that would be a great use case. You would have to put everything back together again, and that would be a nightmare. Now, modern computers today still read data in binary form, but it's much faster and more convenient to read this from electronic circuits or from magnetic or optical disks than paper-based punch cards. And that's going to be the start of Unit 1 for us. Why do computers use binary? Now, if you looked at the previous lesson, you have an idea that human data is analog data and computers use electricity or electronic data, which is 1 and 0 to represent the world. So we've got to work out a way of taking our text, our images, our sound, our pressure, our smells, whatever we want, and convert it into binary data, because the computer will only understand ones and zeros, on and off. So all the devices you have in your computer, cameras, mouse, keyboards, monitor, printer, all talk to each other using electricity or binary data. So what do you need to remember? Well, the key point is that binary data is processed using logic gates and stored in registers. That's where we're going to go towards. Computers use binary, the digits are 0 and 1, to basically store data, and this data is very useful to us. A binary digit, or its short form, a bit, is the smallest unit of data in computing, and it's basically a 1 or a 0. Binary numbers are made up of bits, and an example of a binary number is 1001, and you probably have encountered this before. The circuits in a computer's processor are made up of billions of transistors, which basically are switches, and these are activated by the electronic signal it receives. So registers basically store this data, and their memory and logic gates are used for processing. They're all made out of these transistors. So these ones and zeros are used to reflect the on and off states of a transistor. Computer programs are sets of instructions, and each instruction is translated into machine code and simple binary codes that activate the CPU to do something. And this is normally written in the CPU's instruction set. We'll be talking about all of this later on. Programmers write computer code, and this is converted by a translator, a program which converts whatever the human types in, for example, a print command in Python, into exact binary instructions that the processor can execute. So all software, music, documents, or any other information that is processed by a computer has to be stored or converted into binary. So the second key point here is any form of data, anything you want the computer to process, needs to be first converted to binary for the computer to actually do anything with it. If you don't convert it, it just won't work. And for that, we need to use a number system. And what exactly is a number system? Well, a number system is basically a set of symbols which are used to represent numbers or quantities. For example, the number 1 or the symbol 1 represents just one. The symbol 2 represents two things, and so on. Now, it's possible to represent any possible number with most number systems apart from a one-digit number system, because that can only represent one quantity. The small number systems, for example, binary, which is 2, or perhaps octal, which is 8, they use a small symbol set. Therefore, you need more digits to represent an equivalent number that perhaps you would use in a denary number system or a hexadecimal number system. An example is in denary, 9 is represented by a single digit 9. In binary, 9 is represented by 4 digits, 1001. So you need to take up more screen space to represent the same number. So the key point here is that number systems help in representing all numbers in a small symbol or digit set. So what are the most common number systems? Well, you've heard about binary. This uses a base 2 number system. Base 2 means 2 digits. Denary, also known as the decimal system, this uses the base 10 number system, and this is the most common system that we use because we have 10 digits on our hand, and we perhaps learned to count using that in the early days of our existence. Hexadenary, also known as hexadecimal system, this uses a base 16 number system. And there's obviously octonary, also known as octal. This uses a base 8 number system, so it has 8 digits. Hexadecimal has 16 digits. We only need to know about binary, denary, and hexadecimal. So the key points are binary is base 2, has 2 digits, 0 and 1. Denary is base 10, has 10 digits, 0 to 9. And hexadecimal is base 16, and it has 16 digits, 0 to 9 and A to F. All the other numbers in the world can be represented using a combination of these numbers. For example, 10 in denary can be represented by 1 and 0. So we don't need to have a separate symbol. In hexadecimal, 10 can be represented by the symbol A. So the greater the amount of digits available, the smaller the representation of a big number would be. So it probably makes more sense to have a crazily huge number system. But then you also got to realize that we've got to remember all these symbols. So it's much more difficult for us to remember a base 32 system compared to a base 10 system. Okay, that's all there is to number systems. They just represent numbers in various symbols. However, we need to just focus on binary, denary, and hexadecimal. So we're going to be looking at that. And the next stage for us is to learn how to convert numbers from one number system to another, because everything in the world can be represented in numbers, even text and images and sound, all of that can be converted to number. So what are the steps? Let's start by converting binary numbers to denary, numbers that we understand. So say, for example, you've got a number 0001011. Now, first, we're going to list the binary number exactly. Just make sure you have some spaces because it aids in your understanding of how to use that number. So 0001011, we write it like that. Step 2, we write the correct base 2 headings above the binary code from right to left. The rightmost bit is always 1. And in a base 2 number system, we'll just simply multiply it with 2 because it's base 2. That's why it's called a base 2 system. So the next heading becomes 2 because 1 times 2 is 2. The next heading after that becomes 4 because 2 times 2 is 4. The next heading becomes 8 because the previous heading was 4. So 4 times 2 is 8. Then 16, then 32, then 64, then 128. Step 2 is to write these headings on top of the binary number itself. And then finally, we add up the values of all the headings that have a binary 1 below them. So if you look at our number, the ones are in 16, 4, and 2. So we add them up, and the total number is 16 plus 4 is 20 plus 2 is 22. So the denary value of 000101110 is 22. That's how you convert binary to denary. The algorithm is pretty simple, just 3 steps. What about converting denary to binary? Now, there's a couple of methods you can use, so pick and choose the one that you're most comfortable with. Method 1 involves simply subtraction in a way. So consider the conversion of 107, which is on screen in method 1. You write the binary headings on top because 107 can fit into the 8-bit setting up to 128. So we'll keep writing the headings 1, 2, 4, 8, 16, 32, 64, 128. Why 128? Because 107 is less than 128. Does 128 go into 107? No, it doesn't. Therefore, we write 0 under 128. Does 64 go into 107? Of course it does. So we write 1 and we subtract 64 from 107, which then gives us 43. So we look at the next number, 32. Does 32 go into 43? Of course it does. So we subtract 32 from 43, which then gives us 11 remaining. Does 16 go into 11? No, it doesn't. So we write 0 there. Does 8 go into 11? Of course it does. So we subtract 8 from 11, which leaves us with 3. So we write a 1 underneath 8. Does 4 go into 3? No, it doesn't. So we write a 0 there. Does 2 go into 3? Of course it does. So we subtract 2 from 3, which gives us 1, and we write 1 underneath the 2 column. And then finally, does 1 go into 1? Of course it does, because 1 minus 1 gives us 0, and we write a 1 there. So all of that gives us 107 in binary: 0, 1, 1, 0, 1, 0, 1, 1. Now you could then use the binary to denary conversion method to check your answer. And once you get used to this method becomes very quick if you're very good at subtraction. Another method that you can use is the division method. Now, since we're using base 2, we can just divide the number and just count how many remainders we have left. So let's start looking at a division method. So we take 107, we divide it by 2, that is 53, remainder 1. So we write remainder 1 on the outside of that. Then we divide 53 by 2, which is basically 26. 26 is 52. That's remainder 1 again. Then 26 is divided by 2 again, which gives us 13. Now this time it goes fully into 26, therefore there's no remainder. So we write remainder 0. 13 divided by 2 gives us 2 times 6 is 12, remainder 1. We write that down. 6 divided by 2 is 3, remainder 0. We write that down. And 3 divided by 2 is basically 1, remainder 1. We write that down and we carry on until we reach 0. We then write these remainders from bottom to top. So it becomes 0, 1, 1, 0, 1, 0, 1, 1. And that is the same as the number we got using method 1. Now this is the division method. The first one is subtraction method. Depending on how good your mathematical ability is, whichever method you understand best, you use that to convert denary to binary. Now, when would I use it? For IGCSE exams, I would just simply use method 1. That to me is a lot more simpler. However, if you got complex numbers, for example, really huge numbers, I would probably use the division method for those. Just remember, in the exam, you won't be allowed a calculator, so just pick one method and practice it so you become good at using it. It's pretty simple in the end. It's just a matter of either subtraction or division. Okay, we can convert numbers into binary. But what is this bits and bytes and kibibytes and megabytes and all of this stuff that we hear day to day? Well, in the real world, we normally use prefixes to represent huge numbers. For example, a kilometer is 1,000 meters. So we do the same thing with binary numbers. So we have bits, which is the fundamental or the basic unit, 0 or 1, and 8 bits, a combination of 8 bits, is called a byte. And a nibble is 4 bits. I'm guessing computer scientists love our food jokes, and they've decided to represent some basic units as that. So bit 1, 0, nibble 4 bits, byte 8 bits. So a byte is a unit of measurement of information storage that's equivalent to 8 bits, and it can be used to represent letters and numbers. For example, 0, 1, 0, 0, 0, 0, 0, 1 is 8 bits long, so it's 1 byte and represents the capital letter A in 8-bit encoding, and that's something that's used in ASCII code. So when you press the letter A on your keyboard, it's converted into this binary number and then processed. But that's not enough to represent the bigger numbers. As computers became more powerful, we used more and more data. So we decided to start using terms such as kibibytes or KIB as a unit of data, and that's equal to 1024 bytes or 2 to the power of 10. This is not to be confused by the decimal kilo, which means 1000 or 10 to the power 3. A kilobyte is just 1,000 bytes, and a kibibyte is 1024 bytes. So if you looked at that little pyramid on the top right-hand corner of your screen, you probably can work out why the image is partially incorrect. Think about that by looking at the number system. So we've got kibibytes, which is KIB, which is 1024. And then we have mebibytes, which is 1024 times 1024. So instead of having a million bytes, which is a megabyte, we have slightly over a million because it's 1024 times 1024. So the powers of 2 do not fit into 1000 neatly. Therefore, using the decimal system, which is kilo, mega, in binary is computationally wasteful. But why do we use it? Because it makes more sense to humans. So if you're given a 1 terabyte hard drive, you're probably getting less space than a 1 tebibyte hard drive, which will probably be 1024 times 1024 times 1024. So you get an extra 73 odd million bytes with a 1 tebibyte hard drive compared to a 1 terabyte hard drive. Okay, finally, let's look at bits and registers. Binary is ones and zeros. We can convert numbers into binary. We can have different units of measurements, but we need to store all of this data somewhere. And most of the times we store data or bits in registers. So registers are groups of bits which are used for storage, or they're also used for controlling devices. And it's often depicted as an 8-bit or a 16-bit binary number. Now, these registers are constructed using logic gates, which control the flow of electricity to store the bits, and we know that from the first lesson. The logic gates themselves are made of transistors, which are small devices that allow current to travel. So either they flip a switch to allow current or they turn it off. When computers or microprocessors are used to control devices such as robots, registers are used as part of the control system. So our robot has two wheels which are driven by motors B and C, and the wheel A rotates freely. So these motors on B and C can be controlled. So the first bit can turn the motor on, the second bit can turn the motor off. And similarly, we can turn motor C on and off. The other four bits control the direction the motor spins, either forwards or backwards. And through combinations of ones and zeros, we can turn a particular motor on, we can turn the direction of the wheel on, and the robot can turn or move forward or backwards and so on. You don't need to remember a lot of this stuff right now, but we'll be covering this a bit later on when we look at control systems. All you need to know is that registers store bits, and logic gates are made out of transistors which control electric current. And that's about it. Hopefully, you've learned enough to answer the following questions. What is meant by a number system? What base systems are binary, denary, and hexadecimal? You should be able to convert numbers up to 16 bits. So on screen, there's a 12-bit number, 0011, 1011, 0111 to denary. You should also be able to convert 312, which is a denary number, to binary. So either using the subtraction method or the division method, you should be able to convert that. You should be able to explain what a bit is, a nibble, and a byte is, and how registers, transistors, and logic gates are used in data representation, which means different types of data can be converted into binary and stored for processing by a computer. That's all for this lesson. As usual, if you have any questions, please get back to me, and I'll see you in the next one.